In this video, we're going to talk about boundary conditions, except now we're going to do the magnetic field edition of it. Now recall that so the setup is going to be the same with electric fields. We're going to have a boundary. On one side is one material, mu1. On the other side is another material, mu2. And remember that in electric fields, we pulled two tricks to make this happen, right? First, to find out what goes on in the normal direction, we use some kind of surface integral related rule, right? So we define this closed surface here, and if this is small, the primary contribution of any kind of flux going through these two surfaces will be the portion of the flux that goes through these two surfaces here, right, on either end, because this dimension is really, really small. And so that allows us to relate the normal components across the interface. To have a similar relationship for the tangential components, we did a line integral across the interface, where again, if this dimension is small, then the primary contribution for the line integral will be related to this edge here, and then this line integral, this portion of the line integral over here. So these two segments, and so that allows us to relate the tangential component of the field across the interface. So with that, let's look at what we know about magnetic field flux and magnetic field line integrals. So for the closed surface, for this closed surface here, we know that the closed surface of the magnetic flux density is always going to be equal to what? It's going to be equal to the charge inside, right? But in the case of magnetic fields, because there's no such thing as a magnetic charge or magnetic monopole, the closed surface integral of a magnetic flux density field is always going to be equal to 0. And so what that means is that if this is small enough such that we can assume the field is constant over this very small surface here, that the magnetic flux density, the normal component of a magnetic flux density, times the surface area minus the magnetic field, the normal component of the magnetic field on the other side, times that same surface area is going to be equal to 0. Cross out the small surface area. We then have that the tangential portion of the magnetic flux density is always going to be continuous across the interface. Or remember, we had the normal vector notation way of describing it. We can also write that the vector that is normal to the material interface, n dot b1 minus b2, is going to be equal to 0. Now let's do the same thing with the line integral, right? For the line integral, what rule do we have that's line integral related? Closed line integral related, even. That's right. If we do any closed line integral of the magnetic field, what are we going to get? It's going to be the total current going through that closed surface, right? So it's going to be equal to I. So so if we discretize this, if we say this is small enough such that you can call the field constant, you have the tangential component of the magnetic field on this one side minus the tangential component for the magnetic field on the other side is going to be equal to I, which if we rewrite it in terms of something that will give us a delta L, we get a sheet current density, right? Because sheet current density times delta L is going to be equal to the total current. So if you write it in terms of sheet current density, that allows us to cancel out the L's, and we have the result that the normal component, that the tangential component of the magnetic field, if there's any kind of difference, that's going to resolve itself in the form of a sheet current coming out. So if we were to rewrite it in normal vector lingo, like we did up here, we would have n cross h1 minus h2 is going to be equal to the sheet current density coming out. So if there's any kind of discontinuity between the magnetic field on one side to the other, it's going to resolve itself from a boundary condition perspective through a sheet current density that goes through the boundary along this interface, either going into the board or out of the board, depending on what this quantity over here on the left ends up being. Now, as a review, let's also look into recall what it ends up being in the case of the electric field. So in the electric field, remember, it's a little bit different. Instead of being equal to 0, the normal component is going to be equal to what? If there's any discontinuity, it can be resolved by having a surface charge density along there, right? And then in the case of the tangential component, that's this line integral. This is the Kirchhoff's voltage law equivalent, right? It's a closed loop line integral of E. So we end up having that the tangential component of the electric field is always going to be equal to 0. So there is a kind of symmetry here where in the case of magnetic field, it's the normal component that's always equal to 0. In case of the electric field, it's the tangential component that's always equal to 0. That's continuous across, so the difference is equal to 0. And then if you look at the portion that can be resolved through a surface or current charge, in the electric field, it's the normal component where if there's any discontinuity, it can be resolved by having a surface charge at the interface. In the case of magnetic fields, it's the tangential component where if there's any kind of difference or discontinuity, it can be resolved by having a sheet current run in this perpendicular direction, in this case going into or out of the screen, but along this interface.